This is not a problem from your chapter, but it's a lot of fun. And now that we've covered the concept of energy conservation and we're familiar with the dynamics of circular motion, we're equipped to take a look at this. So this is based on a video posted on Canvas from the show Fifth Gear, wherein, or in this particular episode, a person actually drives a car around a vertical circular track, and they talk briefly about the analysis behind determining the minimum speed at which this car needs to enter the track. There's a minimum speed. Well, there's some concerns about going too slow, and there's some concerns about going too fast. So I'll pull up the video in a moment, and please forgive me. I'm going to be annoying and pause the video at various points to highlight some of the numbers that they mention, and then I'll write those numbers down on this paper, and we'll proceed with the physics.
Welcome back. Right, I'm really excited about this next item because it's the biggest and bestest thing Fifth Gear has ever done.
Hell yeah, check this out. Who remembers these? Hot Wheels Loop the Loop. Come on, Tom, send one down.
There we go.
Yes, but what we wanted to know is, could you do that in a real-life family-sized car?
Yeah, we gave the job to our friendly neighbourhood stuntman, Steve Trulia, but we wanted some questions answering first. How fast would he have to go? Would the car stick to the road? And would he black out under the G-forces? Steve...
So when they say under the G-forces, that's colloquial language, or let's say non-physics class language for the acceleration that the driver will experience. So we'll look at that.
Trulia is the man facing this monster challenge. As Fifth Gear's head of danger, he's rolled, crashed and crashed again in numerous Fifth Gear stunts. But even by these extreme standards, nothing can prepare him for our most dangerous stunt yet. Clearly, scaling a toy up to a record-breaking 40 feet high using 5 tons of steel and a real-life motor was going to be dangerous. So we...
Okay, I believe I heard them say 40 feet high. Let's take a look at the drawing. The 40 feet they're referring to, I believe, would be from the ground to the top of the track. So the diameter of this circular loop is 40 feet, and that would make the radius 20 feet. Now, the first time I tried to analyze this, I went with the 20 feet, and my number didn't quite match the number that you're going to see in the video for minimum speed. And then I realized that I improperly was applying Newton's laws to the car when I really should have been applying them to the driver inside the vehicle. So something I'll look at more carefully later in this video is the fact that the circle traced out by the driver is a little smaller in radius. The person's not actually moving along the ground. They're raised by a few feet off the ground. We'll come back to that.
He sent Steve to Cambridge University's Dr. Hugh Hunt to find out how fast he'd have to go. Now listen carefully.
2r plus a half v in squared.
Starting to cook my brain a bit now.
36 miles per hour.
36 miles an hour.
But you know what we haven't...
36 miles per hour. That seems to be what he's calculated as the ideal speed going into the loop. I'll write that down.
Worked out though is what are the G-forces you're going to experience? Because you want to know whether you're going to black out or not. The total G-force you will experience as you enter this loop will be 6G.
It gives me a bit more confidence because of the science, but at the end of the day, I don't know if that's going to count when I'm staring at the track with my foot on the accelerator.
To lessen the chances of Steve blacking out at the wheel, he needed to get used to pulling 6G. The only place to do that was in this.
Here we go, into the loop! And I feel the G pulling! G pulling my face again!
Stunt Day. The day Fifth Gear finds out if you really can drive a car around a 40-foot-high loop-the-loop. If successful, stuntman Steve Trulia will set a new world record. If he fails and falls out of the loop, the massive deceleration forces as he hits the ground could be fatal. The entry speed is therefore literally a matter of life or death. So Steve verified the car's speedo with GPS,
36, 37,
and then checked again with a calibrated radar gun. 36 miles an hour had been calculated as the ideal entry speed. Slower than this, and he'd fall. Much faster, and the G-forces would knock him unconscious and exert a dangerous force on the ramp's structure.
Okay, let's do the math now. Why don't we first calculate the minimum possible speed that the vehicle needs to have up here so that it doesn't detach from the roadway? I think you have some sense that the vehicle could go faster, like whatever that minimum speed is. If the car is going faster than that, when it gets up here, it'll still make it around the curve, but there would be additional stresses on the track. And you heard them mention that that's undesirable. It's conceivable that the track could even break while the car is negotiating that turn, and that would be bad news. You know, if you've ever been at an amusement park like Six Flags and stood next to a roller coaster with a loop-de-loop, as one of the cars went by, you may have noticed that you can see the track tremble significantly because something as massive as a roller coaster with a dozen or more people in it, that's a lot of mass. And when it's being accelerated at such a large rate, remember V squared over R, the faster it's going, the smaller the radius of the turn, the greater the force you would need to cause that acceleration. So we're just looking for the minimum possible speed, because any faster than that puts more stress on the track, and it also means more acceleration for the driver, which could cause him to lose consciousness. So maybe you know the answer already. I'm just going to quote it off in the corner here. Maybe you already know that you could just set the radial acceleration equal to g. So that's if you're going to the minimum speed, you're letting gravity do all the accelerating, and there's no need for any outside force to do that accelerating. We've seen this a number of times. But let's go ahead and set that up nonetheless. So I'll say at the top, sum of the forces along the r-axis is mass times acceleration along the r-axis. And we've got, I see two possible forces on the person, really. We're not talking about the car, we're talking about the person who's doing the accelerating. And you can see I've already accounted for the fact that the circle traced out by the person is slightly smaller in radius. I'll estimate the difference in just a moment, but the person would be right here at the top, their body. So there's going to be the gravitational force down on their body. I'm sorry, you can barely read that. And there's also the normal force on the person, right? The seat pushing on their butt, pushing towards the center of the circle. Those forces would both be directed towards. Now, if the car was going too slow at the top, you might imagine falling off the seat while you're upside down, and then the seat belt would engage and kind of lift up on you. So in this instance, it is possible to have a normal force that points up, but that would be bad news because that would mean that the car was falling off the track. So we're going to assume that the normal force points down. Normal force plus mg equals mv squared over r. And specifically, we're talking about the speed of the person at time 1. And that's why I'll put the subscript v1 over. And now I'm going to be careful and use that lowercase r. Remember, I used a lowercase r for the radius of the person's circular path. And I'm going to solve this for n. Let's see here. M times v1 squared over r minus g is equal to n. See what I did? I moved the mg over and I factored out n. And here's where we enforce the condition that the car not fall off the track. The normal force between the seat and the person would need to be greater than or equal to 0 in order to prevent that from happening. That's the cutoff speed. Any slower than that, the car would detach. The person would tend to detach from the seat. In fact, if you go with the equal sign, that is the point at which, just for a moment, he's in free fall, because gravity alone is providing the centripetal acceleration. So let's just go with I'll put this added step in here. That means this needs to be greater than or equal to 0, because I could divide by m, right? 0 divided by m is still 0. v1 squared must be greater than or equal to rg. But for minimum v1 squared could be set equal to RG. Again, you've seen it before. And what this really says, well, if I put the R back over here, wouldn't I have V squared over R equals G if I divide by R on both sides? In other words, A sub R equals G. That's the result that I quoted up here. Okay, let's move on to the conservation of energy phase of the problem. Now that we know how fast the car needs to be going at the top, and you know what, it might be useful to calculate that speed just so we have a sense, physical sense of the numbers that we're talking about. Let's calculate R first. Okay. Well, the height of the track here is 40 feet. And I'm going to, let's see, that means that the radius big R would be 40 feet over 2, 20 feet. So from here to the ground would be 20 feet. I'm sorry, that should say FT. But we know that the driver is elevated a few feet off the ground. There's no way that the car is constructed so that he's, you know, just an inch off the ground. He's got to be more like 3 feet off the ground. So I'm going to take that 20 feet and subtract a good 3 feet to give a radius of something like 17 feet. So the radius of the circle traced out by the person is something like 17 feet. 17 feet times, well, 1 meter is equivalent to something like 3.3 feet. And 2 sig figs is fine, because we're just trying to get an approximate answer. 17 divided by 3.35, I'll keep 3 digits here, 3.15 meters. And that would imply that the speed the vehicle needs to have at the top, let me just plug those numbers in, 9.8 times 5.15, I'll take the square root. That would need to be 7.1 meters per second. I'm going to check that. Okay. And now, I guess I'll show you the conversion. 7.1 meters per second times, well, every 1 meter per second is something like 2.25 miles per hour. That's an easy conversion, 2.25. So times 2.25. At the top, they need to be going 15.98 miles per hour. And of course, it's silly to keep those last digits. I could just say 16 miles an hour. All right, well, if the car needs to be going 16 miles per hour at the top, then it definitely needs to be going faster than that at the bottom, because once it starts making its way up the track, there's not going to be the same normal force between the tires and the road. In other words, there won't be as much traction. I hear that word. So I don't think it's possible for the car to continue speeding up on the way up. Whatever kinetic energy or mechanical energy this car is going to have on the way up, it has to already have that on the way in. It needs to achieve that speed. We can't count on the car being able to accelerate anymore with the gas pedal on the way up. So as the car enters the loop, it's got a certain amount of mechanical energy, all of it in the form of kinetic energy. That's if I put the origin down here. If I choose to say y equals 0 down here, then using mgy, we can see that the potential energy of the person is 0 at the bottom. And as the car rises, the person is rising with it. The person would be losing kinetic energy, but gaining potential energy. So the gravitational force is doing negative work on the person, and that's transforming their kinetic energy into potential energy. But we still need to have some leftover kinetic energy up here at the top. So we'll start with this statement, that the work done by external forces would be the change in total energy of the system. What is the system here? Well, that's a little up for debate. Sometimes it's not too obvious, but for me, the system is the person. What are the forces doing work on the person? Let me just draw the person at some arbitrary position on the way up. I see gravity pulling down on the person, and I see this force. That would be the normal force from the seat on the passenger's butt. And that's not doing work because the instantaneous displacement, dr, is that way. So n dot dr is 0. That means the work done by the normal force of the seat on the person is 0. So we don't need to worry about that. Now, you also would have to account, if you really wanted to be precise, you'd have to account for the work done on the car by air drag and friction. There's got to be some rolling friction between the tires and the road, and air drag on the windshield, for instance, or just on the body of the car. But we're going to approximate that as 0. Basically, we're asserting that it's negligible. And again, I'm going back and forth between treating the car as the system and the person as the system. I believe that's valid because of this fact that I just pointed out, that the normal force of the seat on the person should be perpendicular to the person's displacement. So I'm going to go with applying Newton's laws and the energy conservation principle to the person. Okay, well, there is no external work because the only force on the person really is gravity. Well, at least that's the only force doing work. Delta E thermal, remember there are 2 pieces here, plus delta E mechanical. And again, I'm not acknowledging any significant dissipative forces on the person. There's no friction between the seat of their pants and the chair or the seat of the car that's doing, dissipating energy thermally. So we don't have to worry about that. And so we're really just saying that the change in mechanical energy is 0. Mechanical energy should be conserved as the car goes up the loop. That's the same as saying that the mechanical energy at time 1 is equal to the mechanical energy at time 0. It's not changing. Well, we've got kinetic energy at time 1 plus potential energy at time 1 equals kinetic energy at time 0 plus potential energy at time 0. And truthfully, you don't need to go through this exact sequence of statements to arrive here. You could have said something like, no significant friction or air drag, the person's mechanical energy should be conserved. You could write that as a sentence and then jump straight to here. This is a perfectly valid starting place. Okay, the kinetic energy at the top, we can express in terms of the speed of the person at the top, and this is the person's mass, not the car's mass. And then we need the potential energy of the person at the top. I'm going to go back to the picture here, and really I should modify where I put my origin, because now I'm looking at the person's circular motion, not the car. So I really should put the origin at their lowest point, which is the 3.3 feet or 3 feet above the ground. Okay, so that way their position at the top would be 2 times little r. Little r plus little r, that's 17 feet times 2, or in other words, 34 feet. So mg times 2 times little r, that's their height above their starting point. And then their kinetic energy on the way in would be the 1/2 mv initial squared. That's their speed at the bottom here. So I'm assuming they've already reached top speed here, and they maintain that speed as they enter the loop. Then they begin to slow down. And we don't have to worry about that, right? Because of our choice of origin, we put the y equals 0 level at their the place or the point at which they enter their circular path. How can we simplify this? Each term has an m. Let's get rid of that. And let's also get rid of the 2. So, because what we're solving for is the initial. That's what we're doing right now. How fast do they need to be going on the way in? So I want to solve for v naught. I'll multiply this whole thing by 2 over m. I get v1 squared plus 4 rg equals v naught squared. Now we're getting somewhere. We could have plugged in numbers already, but it's nice to do things algebraically. So the square of the initial speed needs to be, I'm just flipping the 2 sides, and here's where we can substitute. We already found the necessary speed at the top. And instead of plugging in the numbers, why don't we just write that again in terms of r and g? That will allow us to simplify the algebra. So when we square v1, we get rg. Instead of writing v1 squared here, I'll go with rg plus the other 4rg. And that means we're dealing with 5rg. And I believe I did see a 5 on the whiteboard where they showed that that instructor working out the details. Okay, so we've got 5 times 17 feet, but remember we need to use SI units, so I'll convert once again. That's 1 meter for every 3.3 feet, and then our 9.8. If I plug SI in, I can expect SI to come out. Don't forget to take the square root. I find that they would need to be going 15.88. I'll go ahead and keep those digits for now. 15.88, or 89 really. I could have just rounded this to 15.9 meters per second times, once again, every mile or every meter per second is something like 2.25 miles per hour. So times 2.25, here's where I will round. Hey, check that out, 35.7. Let's just round that up to 36 miles per hour. Just like the number quoted by the professor that they consulted in the video. So I'm assuming that that instructor used the exact same analysis we're using here. I mean, what else is there? Okay, that's not everything we can say about this problem. They also talked briefly about the so-called G-force subjected to that the driver was subjected to on the way into the loop. Now, the driver would be accelerating the whole time, but the greatest acceleration happens right here because they're going the fastest at that point. And when they talk about G-force, my interpretation is this. They're really talking about the person's perceived weight, how heavy they feel. And that is what we call the normal force. So, you know, if you're just standing on the ground and you're not accelerating, the ground pushes up on you, gravity pulls down, and they would have to balance. So under usual circumstances, when you're just standing there, you feel heavy. Well, your normal sense of heaviness is just mg. But let's calculate the normal force on the person as they enter the loop. So the G force at the bottom. Okay, now they're not actually moving in they haven't executed a circular path at this point, but as soon as they've crossed this point, they are now in circular motion. Hopefully you can understand that. You don't actually need to trace out an entire circle to be in circular motion. You just have to be on a trajectory that is part of a circle. So they're already accelerating at this point because the track is bending upwards. And I'm talking again about their body, not the car. So here's the seat pushing up on them. Here is gravity pulling down. This is the person's mass. And I know that N has to be greater in magnitude because the net force must point towards the center of the circle. It has to be centripetal. And we go back to this starting point. N minus mg. Now this time I'm not going to set the normal force equal to 0. That was what happened at the top. But obviously we're talking about something different at the bottom. So this is V initial squared over R. Okay. So this will tell us once I plug in numbers, this formula will tell us how hard the seat is pushing on him. In other words, how heavy he feels. And I believe that's what people usually mean when they talk about the G forces. I don't actually need to plug in V naught, I don't think, because didn't we already find, yes, V naught squared is 5rg. So V naught squared over R, we would divide out the R, that's just 5g. So this is m times g plus 5g. How nice is that? There's our 6 times mg. So when you heard the person in the video say that the driver would experience 6 g's, what they mean is their perceived weight, or maybe I don't even need to use the word perceived. Your book actually does use the word weight to mean normal force. Their weight would be 6 times what it would be typically if they're just standing on the ground. There's your 6 g's. Okay, so we've corroborated everything said in the video. Now, why wouldn't you want to go any faster than that? Again, look at this formula here. If your initial speed was greater than 36 miles per hour, it means you're going to feel more g's. Instead of having a 6 out here, you might have a 7 or an 8. And that becomes dangerous. If you want, browse YouTube, pull up videos of pilots training and subjecting themselves to high accelerations. And you can watch those videos where the people pass out. And they usually pass out by the time they get up to 7 or 8 Gs. A lot of people will last to 9 Gs, but that's really the point at which practically everybody seems to pass out, even if they're trained pilots and they're doing those things like, flexing certain muscles or tensing their, I forget how it's done, but there are some ways you can cope with the acceleration. But beyond 6 Gs, you definitely run the risk of passing out. And you might want to read on Wikipedia, if you're interested, about G-lock experienced by pilots sometimes. Gravity-induced loss of consciousness. There's some interesting telltale signs when you're nearing G-lock as a pilot. Like I think you lose your color vision first. Perhaps the blood is draining from your retina, and so some of your light-sensitive cells are not working the same way. Or maybe it's the optic nerve, I don't know. And I think, yeah, there's some other interesting symptoms. So pilots know when to ease off the throttle, so to speak. The last thing I'd like to look at is just a simple explanation for why you might tend to lose consciousness here. I'm not going to be able to draw a very good picture, but when you enter the track, okay, I'm going to make a cartoon person here. Just think about the person's head. It's gross, but your head has fluid in it, right? There's blood and the cerebrospinal fluid. So gross. That's one reason I quit psychology years ago. It's because I was tired of thinking about fluids inside brain cavities. But the blood in your head is moving this way. And remember Newton's first law? I got to mount this camera better. Newton's first law says if there's no force on something, then the acceleration is 0. In other words, that object will just continue with constant velocity. That means either stay put, don't move, or move in a straight line at constant speed. Newton's first law arguably is contained within Newton's second law. So the blood in your head has inertia. It's going this way. But as soon as you enter the loop, the car is forced to accelerate upwards by the track. And since you're in the car, you're forced to accelerate upwards by the seat pushing upwards on the seat of your pants. And then, of course, your head, which is attached to your body, it gets accelerated by your spine. You know, the bones in your neck are pushing your head upwards. But what about the blood? Well, again, the blood in your head has the tendency to just keep going forward. So it's kind of like your head goes up, but your blood doesn't initially until it's strange to think about the details, but something's going to have to push on the blood in your head to get it to accelerate upwards. And there's probably a little bit of a delay there because it's a fluid. So the tendency is for the blood to drain from your head. And that's why you may tend to lose consciousness. Now, if you look at a roller coaster, you might get the opposite effect depending on whether you're going through a dip or over a crest. So if you're going through a dip in a roller coaster, your blood was headed that way, and then you forced your whole body to go up. So the blood keeps going down, and it would tend to leave your head. That's where you might feel faint, or you could even pass out if you're going fast enough. Wouldn't that be an interesting thrill ride where the engineers or maybe somebody at the controls is messing around? You make the thing go so fast that practically everybody passes out on the way through this dip here. Over here, something else happens. Here's your body. And on the way up, everything in your body had this velocity, including the blood in your head, but suddenly your body is yanked downwards, and the blood in your head's not going to catch up immediately. So the blood would have a tendency to go up into your head, right? Your blood continues to go that way. It's got inertia, Newton's first law, but your head is being forced to go down because obviously your head's not going to separate from your body. I think you'd have to have the roller coaster going really fast to accomplish that. Okay, so those are two different effects. I don't think that would make you pass out, but it might be uncomfortable. Perhaps the pressure in your head would go up. So one idea I've heard, let's imagine this is the circular path traced out by an airplane. I can't draw airplanes. Okay, that's passable. What if this person was doing a dive or a turn in their plane, their fighter jet, whatever? I know this is silly. their head would probably be up here in the cockpit, and it wouldn't be outside the plane. But it's the same effect as right here, is it not? On the way down, all the blood in the person's head would have a velocity in this direction, but then the plane is forced to rise, and the blood would tend to drain from the person's head, and they might lose consciousness. So what if, because people have talked about this, what if you could change the way a person is their posture, the way they're seated within the plane? What if they could ride in the plane like this and have some kind of a headset on? You know, who needs to actually look out the windshield, right? Just have really special cameras that are giving you live video feed. You know, there's always the risk of the internet not working or some technical difficulties, so I wouldn't want to do that. But you can see that if you were able to pilot a plane while lying on your back, then that would reduce some of the effect here, because instead of the acceleration, yeah, this is really what it comes down to. The acceleration is that way, right? At the bottom of the circle, it's towards the center. That acceleration is lengthwise along the person's body. That would tend to make them pass out. But here, the acceleration is perpendicular to the body. So there's less of a tendency, or really there's no tendency for blood to go from here to here. You would need the blood to be rushing to the right in order for it to be inducing loss of consciousness in this person. So who knows, maybe that's something that'll happen in the future. But the more likely scenario would be drone wars, right?